So hello everyone, welcome again to the next lecture, which is hierarchical control of microgrid. So we'll discuss, as we continued from the last session, basically the uh, coordinated control of multiple sources in a microgrid. So before that, I will continue the discussion where I left in the last lecture about the microgrid stability. That will give us an idea of how the microgrid stability issue arises and why it is important to have a coordinated control in a microgrid. So when we talk about microgrid stability, as I told, it can be divided into either control system stability or it can be divided into power system, power supply or balance stability. So let's see these one by one now. The first is the power supply and balance stability. So the power supply and balance stability is basically related to the maintenance of power balance, effective sharing of power among multiple sources. So basically the whole active and reactive power management is important here. For example, let's say you have 10 or 5 or any number of sources in a microgrid, for example. It should not happen that few of them are getting overloaded but others are not being utilized. Everyone has to be properly utilized so as to have, everyone should have equal reserve available. So that balancing would help in maintaining the stability of the system. Why do we get these stability issues related to power balance? This can happen because of due to the loss of a generating unit. When the power is not balanced properly, what happens? Let's say if there is a generating unit trips. What if the generator delivering the maximum power trips? It will lead to a large transient in the system. So we should try to maintain a balance of power among the multiple sources. Okay. Then sometimes if we violate a DER power limits, just like a synchronous machine has got a capability curve, an inverter also has got a capability curve. Now what happens if you try to overload? Synchronous machine can still be overloaded up to certain extent. But if an inverter which carries basically power electronic devices cannot be overloaded. Instant overloading can lead to failure. So overloading of distributed energy resources can lead to failure. Then power sharing among multiple DERs is important. So power sharing is a very important concept, and that's why in this today's lecture we'll talk about the power sharing requirements. Power sharing means, for example, let's say there are 5 number of sources. All 5 should be equally loaded ideally. It should not happen that only 3 of them are giving power and 2 are not utilized. Okay. Then sometimes to handle the variation, we have a slack generator. You know, PV, PQ, slack bus. The slack generator is basically the one which handles the variability, right? So it has to be usually the highest rated generator so that it can handle the variability. If you do not select the slack generator properly, it can lead to stability issues. Okay. Then no fault load tripping. Sometimes what happens, there is not a fault, but still there could be some other reason due to which there is a tripping. It's called no fault load tripping. So this is not good because the load wants a power supply. Even if there is no fault and there is tripping, it leads to certain issues. Okay. So the supply and balance stabilities are basically divided into 2 main categories: frequency stability and voltage stability, just like a conventional power system, as you are aware. The frequency stability, why it happens in a microgrid more? Because of particularly low inertia. Because in microgrid, most generation are inverter based sources. We have very few rotating sources like the diesel generator. So when there is a large sudden load change or perturbation in the system, the inverter based sources usually don't provide inertia. Then we can add virtual inertia and also a different story. But if usually they are at MPPT or things like that, then they don't add inertia to the system. It can lead to large frequency variation. That automatically means if there is large renewable integration, so the renewable will not add large inertia, and also the renewable will have variability, sudden power change. So the ramp thing that we discussed. So sudden power change again can lead to frequency stability issues because certain power will lead to frequency deviation, and the frequency deviation exceeds certain band. Your protection system can kick into picture. Some trippings may be there, or your frequency may fall, it may collapse, things like that. Low number of generator units in microgrid, because in a traditional system you have large number of generators. Even if one is out, there are others to handle. In a microgrid you have anyways less number of generators, and then if one is out, so you feel in a very critical situation. So that's why the stability is challenge. Other interesting problem that occurs in a microgrid is this. It's called a strong coupling between voltage and frequency in microgrids. Now see what happens in a traditional microgrid. We mainly talk about the transmission system or high primary distribution level where the X by R, the line reactance by resistance ratio is high. The line is mainly inductive in nature. If the line is mainly inductive in nature, we say the frequency and voltage are decoupled. The reactive power affects the voltage and active power affects the frequency. The decoupled nature is there. Why that is there? Because the line is inductive in nature. You must have read the formula P equal to EV by X sine delta. Right? So EV by X, we take the line as X. Okay? And then we say for small deltas, P is proportional to sine delta, so angle affects the power. When we talk about a microgrid is mainly at distribution level, where the line is no more reactive now. The resistance also plays a role. As the resistance starts to play a role, the voltage and frequency will have a coupling now. So it's not that the active power will affect only frequency or the voltage will only affect the reactive power. So what happens then, if there is a frequency deviation or voltage deviation, it leads to other effects also. So for example, let's say there is a reactive power issue. There is high demand of reactive power. If there is a high demand of reactive power, what happens? The voltage will come down. But the voltage change will then lead to power change. And power change will then lead to frequency change. So all of them are integrated. That's why in a microgrid, a strong coupling between voltage and frequency in microgrids is there that leads to frequency stability. Then a small scale of microgrids. As I told, there is in a conventional power system you can have multiple generators. In a microgrid you can have only few generators, few rating, small capacity. So what happens then, if one of them is out, others have to handle the variation, and it can lead to stability issues. Poor coordination of multiple frequency control and power sharing among DERs. So now we'll see, as I told, so far what we have read is the control of one inverter. But when there are multiple inverters, have to be properly coordinated, so they power sharing equally. They share and they properly together regulate the frequency. If they don't do so, what will happen? There are chances of frequency instability. Okay. Then insufficient generator reserve. So in a large conventional power system, we have sufficient reserve, which we call them spinning reserves. In microgrids, usually the reserves are less. We may have certain battery as storage, that's it. Otherwise, we don't have much reserves. And if you don't have reserves, there is a certain power demand. What will you do? Lead to instability problem. Alright? Okay. Reason for reactive power stability concerns. Again, similar to the active power sharing, there could be reactive power sharing issues because it may happen that one source is delivering most of the reactive power, other is not delivering reactive power, and if for some reason that source is out or something happens, then lead to stability issues. Again, as a synchronous machine has got a capability curve, it has got limits how much active and reactive power it can supply. Similarly, this also a DER also, inverter based sources also will have active and reactive power capabilities. So if the limits are hit, you cannot supply the reactive power. Okay. Now, another thing is, in a microgrid, the sources are quite close to each other. So the physical distance or the physical impedance between them is small. If the physical distance or impedance between them is small, what happens? Even for minute variation, there is large inrush current, circulating current. So those can also lead to stability issues. Okay. Then usually when we talk about power sharing, we will subsequently read in this lecture, we go for a control which is called a droop control. And if the droop settings are not good, the voltage may fall due to large reactive power. So the droop setting may affect your reactive power, the reactive power, that means the voltage that is associated with the reactive power, the AC voltage. On the other side, you can have then the DC voltage limitation also, the DC voltage stability also. What happens if there is a, for example, take like this, you have a, you know how a PV characteristic looks like, something like this. Now for some reason, if you fall on the left hand side of the MPPT point, it's an unstable equilibrium. The DC voltage, the PV voltage can fall, it can collapse. So due to certain regions, if the DC link capacitor voltage collapses, then it's the voltage stability, but the DC side voltage stability. Okay, and then again, always in the system there can be small or large disturbances. Those disturbances can lead to more stability problems. Okay. So this, as I told, this is like a classical power system stability, which is the frequency and voltage stability. In a microgrid, what is more important is the control system stability. Okay, so the control system stability may arise due to inadequate control schemes, and that is important. The control has to be proper. Try to understand. So there are so many controllers. For example, we discussed today the inner loop control, the outer loop, the inner loop, outer loop, the current control and the voltage control. What if they are not properly tuned? What if the controllers are not properly tuned? So that may lead to control system stability. Okay. Then there could be harmonics. So if your controllers don't suppress the harmonics properly, then there could be harmonics that can lead to resonance, and then there could be stability issues. So it's not due to the energy balance problem, it is because your control is such that it is leading to a resonance. Because see, in your circuit you have so many RLC, filters, parameters, line resistance, inductance, those things, and there could be LC oscillations, right? Why these oscillations are arising? Because your controllers are injecting some frequencies which may excite certain modes of oscillation or certain resonating frequencies. Okay. Then certain stability issues can arise due to, as I told, LCL filter, inverter control machines. There could be issues between, let's say, a machine and an inverter working together. Their controls are not properly coordinated. Then there could be issues. Okay. So whether it is machine or it is inverter, their controls are important, and that is why it is categorized into two categories: either electric machine stability or the converter stability. When you talk about the electric machine stability, in electric machine, there are two main things. One is the excitation system and one is the governor system. Okay. So if you do not design the excitation system properly and the governor system properly, you may have certain issues. For example, in a classical power system, if you have read a power system dynamics course, for a high gain AVR can lead to small signal stability problems in a SMIB system kind of thing, like, and then we use a power system stabilizer. Why? Because the exciter is a high gain exciter. High gain excitation system may lead to instability. That's why we use a power system stabilizer. Similarly here, you have an inverter, you have a machine will have its own excitation system, machine will have its own governor system. The governor is to regulate the active power, excitation, reactive power, you know that, right? So the controls of the excitation system and the governor system have to be properly designed. That's the main thing about machine, that's it, no more. Talk about inverter stability issues. From the control system point of view, there can be many. So a lot of stability issues can arise from the inverter. Okay. For example, the inverter's inner voltage and current loops that we discussed just now, they can lead to some instability. Why? If the gains are not properly tuned. Alright. Or what if there is a large disturbance in the system and your control is not good enough and it leads to over voltage, under voltage, over frequency, under frequency, things like that. Now what happens if such situation arises? Your protection system will kick in. And what the protection system will do, it will lead to tripping. Let's say DER trips, something happens, and it will lead to, again, It's like a blackout. So it's the instability problem. Okay. One very important problem that arises due to the controls of the inverter is this: the low frequency oscillations. The low frequency oscillations are mainly caused by the power controllers. So far we have just discussed the inner loop and the outer loop, which are related to just one single inverter. But we have not yet discussed how the inverters share power with each other. So as I told earlier, none of the inverters should be overloaded. All the inverters should have equal loading. They should supply equally to the power. So the point is, how do we make the powers equal? There are power controllers. Okay. If those are not designed properly, then it leads to low frequency oscillations. And low frequency oscillation may become unstable. Next, your inner loops may lead to high frequency oscillation. So your voltage and current control loops that we discussed, they may lead to harmonic instability, high frequency. While the power control loop that we will discuss subsequently, we will lead to low frequency oscillations. Okay. Then, if there are multiple sources, it may happen that there could be multiple resonating peaks. That's in the system. It's not just there is just one resonating frequency. The system can have multiple resonating frequencies depending on the multiple combinations of RLL or multiple inverters. So if those frequencies are there and those frequencies are excited, those resonance or harmonic instability issues can arise. Okay. And then the harmonic instability or high frequency switching, high frequency instability can also arise due to the high frequency switching. There are series and parallel components, there are parasitic components, parasitic capacitors and all. Those LC oscillations can again lead to some high frequency oscillations. So the whole point is, considering all of these things, that it is very important that we design our controllers to meet all these objectives. Obviously, voltage regulation, frequency regulation is the first thing. But then power sharing, active power sharing, reactive power sharing, DC voltage stability maintenance, harmonic mitigation, all of these things are very important to maintain the stability of the microgrid. Okay. And that is where the control plays a very, very important role. And then if you talk about a grid connected microgrid or a grid connected inverter, you have a PLL. PLL itself can lead to instabilities, because PLL has got a PI controller. You have to tune the PI controller. So if it is not properly tuned, or it is not able to track the phase angle properly, because the PLL gives theta, it takes input VABC. What if the VABC is unbalanced? Okay, which, let's say, unbalanced, or if there is a transient voltage deviation, and the PLL in those transient condition fails to properly give the phase angle information. If the PLL fails to give the phase angle information, what can happen? The subsequent control can get affected. The subsequent control can get affected, lead to some kind of stability issues. So PLL creates some stability issues, like it fails to track the phase angle, or its bandwidth is not sufficient enough to handle the dynamics of variation of the voltage and all those things. Okay, so the whole point is the PLL also has to be properly designed. The control, not just of the inner loop or the outer loop, but every aspect of the control has to be properly designed. And then, as we discussed the classification, we went down, we discussed there could be a small disturbance and there could be large disturbance in the system. So the small disturbances, the large disturbance are the one which for which we have to go for nonlinear analysis. Linearity is not maintained, and typically these are large perturbation in the system, like some short circuiting, like some transition from grid connected mode to islanded mode, or islanded to grid connected. That means there's a grid is being connected or disconnected. So there is a sudden change like that. Okay, there could be a loss of generation. Okay, and or if like any other kind of fault or whatever you can think of. So what happens if there is a large perturbation? It can lead to large frequency oscillations, voltage oscillations, or it can lead to improper coordination between the distributed energy resources. Okay, A small disturbance, as I told earlier, it is not just by the size of it, is definitely the perturbation is small. Technically we call it small perturbation when the system linearity is maintained. In that case we can go for linear analysis like the eigenvalue analysis. Okay. So to summarize the problems that can arise due to the stability issues of a microgrid is basically either the control system stability or the power supply and balance stability. The cause, as you can see in this table, for electric machine stability, it could be poor controller tuning, either the excitation system or the governor system. For the converter, there could be many things, for example, poor tuning, PLL problems, harmonic instability. For the power supply problem, it could be voltage stability or frequency stability, as we know. As we discussed, voltage stability could be due to reactive power problems, inadequate reactive power supply, you don't have a source of reactive power, like that, okay. Or you can have frequency stability problems, that some sources have hit the active power limit, the sources cannot provide the active power even more, or the active power sharing is not correct, some is getting overloaded, some are underutilized, okay. So these are the root causes of the stability problem. What happens due to these problems? For example, if you talk about a control system stability, and if you talk about the electric machine stability, where the controllers are not properly tuned, it can lead to undamped oscillations or aperiodic voltage or frequency increase and decrease. Okay, so this can happen because there could be oscillations and the voltage and frequency can change. Like when you talk about the converter stability, again, if these are the problems, that if the PLL is not well tuned, the PLL problem, synchronization problem, it can again lead to some undamped oscillations, low frequency oscillations, like that. Voltage stability issues due to the power supply problem, as I told earlier, it can lead to voltage stability problems in the AC side as well as in the DC side. So it can lead to ripples or fluctuations in the voltage, in the DC voltage or in the AC voltage, or it can lead to complete failure of the DC voltage. That is also possibility. Okay. Frequency stability, as we told, it is mainly due to the active power balance thing, and if it is not done properly, it can lead to large rate of change of frequency. So when you talk about frequency, the frequency is important, but at the same time the rate of change of frequency is also important, right? So it can lead to large rate of change of frequency, or it can lead to steady state frequency deviations, power swings, frequency swings. Those things can be there. Okay. So these are some major problems. Another problem that arises, particularly in the grid connected microgrid, is the stability issues with weak grid integration. So now what happens, you remember the figure that we discussed in the previous lecture, there is an inverter is connected to a grid. The grid would regulate the PCC voltage, the point of common coupling voltage. Now what happens if the grid is not strong enough? That means, let's say there is a large impedance in between. Simplest example, between the point of common coupling and the infinite point, there is a large impedance, let's say. So then the current flows, this I into Z deviation will lead to voltage deviations at the point of common coupling. As the voltage deviates, then the controller can get affected, because the control that we have developed is basically on the principle that the voltage is nearly constant. It's maintained constant by the grid, so that the inverter is basically a current source. But now the inverter is a current source, while the voltage is no more regulated properly. It's a weak grid, the voltage can change, so then the voltage can change. Alright. Because the voltage can change, the current injection can lead to change of the voltage. So now the voltage itself has got changed. So how do you know how much current you have to inject? So the control can get affected. Getting my point? So that is why in a weak grid, when the grid is not strong, they can lead to your active power flow or reactive power flow can lead to stability issues. So what the summary of all of this is, that a microgrid, and now particularly in this lecture we'll talk about the autonomous microgrid. In a microgrid, when we talk about the stability, the control plays a very important role. Okay, and that is why we have to focus on developing some coordinated and proper controls of AC microgrid. So we'll talk about AC microgrid. The concepts are easily replicable for the DC microgrid. Clear? So now we talk about the AC microgrid. Our microgrid control basically means to have a coordinated control among multiple sources or multiple inverters connected in a microgrid. Okay. Now take for example, we discussed in the previous case, let's say we have an inverter, it is being operated at 50 Hz. Well, it will be very well, it will work at 50 Hz, this is not a problem. But then suppose there are 4, 5, 6 inverters, multiple inverters, and each one of them are working at their own frequency. Okay, well and good, if they are working well and good, but the problem is, to in AC system to have a proper synchronization is not just the frequency but the phase angle as well. Yes. So one is the synchronization thing out there. Second thing, it may happen well and good, still let's say they are working fine, but then it can lead to overloading. Why it can lead to overloading, I'll just discuss in just a couple of slides later. Okay, this way. So it can happen that one of the sources is getting overloaded while the other is not properly utilized. Okay, that should not happen. So all the sources in the microgrid have to be coordinated properly. And the coordinated control, the objective is basically, well, definitely first and foremost, the objective is the control of voltage magnitude and frequency. Those are the two very important things. So because in an AC system, microgrid system, there is no grid that regulates the voltage and frequency. So definitely the inverters has to regulate the voltage and frequency. The second thing is the active and reactive power sharing. As I told, it should not happen that one source is getting overloaded. So it should be a proper sharing. Then higher level objectives like optimal power flow. The power is flowing. You have to have optimization. Which source is best to give power at what time? Demand side management. Say evening hours. The peak is going to come. Whether you want to keep the battery charged, not charged. All those things are further higher level control. But the basic minimum things are these. You have to control the voltage magnitude. You have to control the frequency. You have to control the active power sharing, reactive power sharing, and all those concepts. Now, when you talk about the active power, the voltage magnitude control is basically by the control of D axis voltage and the Q axis voltage, VOD star, VOQ star, that we just discussed in the last lecture. So what we do, we align the voltage along the D axis, Q axis voltage is basically maintained at 0. Frequency control, very simple, it's an inverter, it can produce its own frequency, it doesn't need any frequency reference. So what it happens, you generate your own omega frequency, 50, 2 by 50, integrate it, you get theta. So what is the physical significance of it? The theta that we are talking about? That theta is when you finally convert dq back to ABC. So dq back to ABC, the ABC quantities will have a phase, because any sinusoidal can be written as Vm sin omega t. That sin omega t term which is there, omega t, that is the theta. So with what theta that we give to the conversion from dq to ABC, that theta is basically used and you get the sinusoidal quantities. Alright, and that theta for an autonomous system we get by integrating its own frequency, so you get a constant frequency. So that is how the frequency is maintained in an inverter. But then the problem comes that how do you maintain active power sharing and reactive power sharing within multiple sources? That is one thing that we have to decide. So to achieve that thing, we have different types of controller. These are called centralized, decentralized, distributed, or master-slave approach, hierarchical approach. I'll discuss this one by one. So centralized, decentralized, distributed, keep these on hold for certain time. Let's talk about master-slave approach and hierarchical control. When you talk about a master-slave control, as the word speaks, there is a master, others are the slave. That means one unit is the master unit, you can say it's the highest power rating unit or something like that. That unit will decide what others have to do, how much power the others have to inject, something like that. Or at what ramp rate they should change their power, or how much is the reactive power the others should operate. So basically the commands are given by the one master unit to the other slave units. This is called a master-slave approach. The problem with this is, if you don't have the master, okay, then the slaves are lost. They don't know what to do. No one is guiding them then. And what is the meaning of the master is lost? It's basically, for example, let's say communication failure. So the master is communicating with all the slaves, but there is a communication blackout between the master and the slave. Now, slaves do not get any command from the master. They can't operate. So the other units which are dependent on the master unit, those units do not operate well. So this is one approach. It's called a master-slave approach. Another approach is called a hierarchical approach. This is a proper defined, well-defined hierarchy. You understand hierarchy is there in any organization. No? There is one top body, then the next level, the next level, the next level. So that type of hierarchy is what we use when we go for a microgrid control. Alright. Let's see this. The hierarchy of a microgrid is divided into three main levels: the primary level, the secondary level, and the tertiary level. Okay. When you talk about the primary level is basically the first level, and the objective of the primary level is to achieve the desired active and reactive power sharing. That means, for example, let's say there are 10 sources in the microgrid. Your load is, for example, 10 kilowatt. Then what do you want? Each source should provide 1 kilowatt of power. Okay. Then what happens? How do you ensure that each source provides 1 kilowatt of power? That ensuring is done by the primary control. Okay. So the primary control is basically the one which focuses on the power sharing. Alright. The secondary control is the one which focuses on frequency and voltage regulation. Because at the end of the day, you do not want your frequency to deviate. You do not want your voltage to deviate from the nominal value. So the regulation has to be maintained. Okay. And the tertiary level is basically your optimization level, where you achieve a desired cost, for example, minimization of cost, operating cost, economics constraints, all those things. So that is why the tertiary control is the slowest control. It is kind of done in an interval of like 15 minutes, like that. It's slow control. It's just giving the set point which gives you the best optimum value, just like the classical power system OPF study that you do. The secondary control is faster, in the order of few seconds and minutes. It's basically to restore, to maintain the frequency is maintained at 50 Hz, for example, and the voltage is maintained at the rated voltage. Okay. Primary control is a faster control, the fastest of all. It works in the order of some seconds, few seconds only it takes. Its objective is to get the desired frequency and the desired active and reactive power sharing. Okay. This is the hierarchy. Above this there is one also, but sometimes we don't write it. If you want, you can write it. It's called a global. So it's basically global is to achieve the coordination between microgrids. So what we have discussed so far, the primary, the secondary and the tertiary, is the coordination within the microgrid. But if you have to have a coordination among the microgrids, there is one microgrid, the second microgrid, the third microgrid, then how much power flow has to be maintained from one to another to second to third, third to first. That coordination is basically done by the global control. But if you talk about within the microgrid, then the primary and the secondary and the tertiary are the hierarchy. Below the primary, you have the local, which is basically your voltage reference, the voltage controller, current control that we discussed in the previous case. The question comes, this local control is basically controlling the VOD star, VOQ star. The question is, what is my VOD star value? As I told, VOQ star is maintained at 0. You get the voltage aligned along the D axis, the Q axis reference voltage is set to 0, and you have all the voltage along dx's, right? Now what is the value of this? How much value we give this? For example, if you don't go into details, just think logically. What is the voltage magnitude you want at your homes? Is as good as 230 volt AC phase, single phase, right? So there are some standard voltage that we know. We can keep these values, okay? But then these values will not lead to the desired power sharing, active or reactive. And that is why the VOD star, the actual reference comes from the higher level. So the higher level gives a command to the lower level. So the primary control gives command to the local controller. The VOD star should be this much, or your frequency should be this much. The secondary control gives command to the primary control, gives reference to the primary control. Why? The secondary control will say, it's fine, not a problem, you can have your desired power sharing, but I want the frequency to be restored while you achieve your desired power sharing. The frequency should not deviate. Okay? So the secondary control will give that command that restores the frequency or the voltage deviation. Okay? The tertiary will then give command to the secondary that okay, fine, we have to do all of these things, but we have to keep our other objectives in mind. Could be harmonic minimization, could be grid support, could be optimum power flow, things like that. So this is the basic hierarchy of it. Now, why do we need this hierarchy? Because otherwise the microgrid will not work properly. So we will discuss these hierarchy in just in this unit one by one. The global, as I told, is just to have the optimization within the within multiple microgrids. So it's like an optimal power flow or some contract based power between two microgrids. That's it. It's nothing much to discuss here. The tertiary, as I told, is just like the OPF or those kind of things. So it is runs in 15 minutes. You run an optimization model, loss minimization, cost minimization, something like that. And that is all. The important ones are these: the secondary control and the primary and the local. Okay. Now the local is the one which maintains the desired voltage and the desired frequency at VOD star at some value and VOQ star at some value. The question is, how do you get that value? And then it maintains certain output frequency, 50 Hz. How do you know that you have to maintain 50 Hz? Do you think 50 Hz is the best case, or do you want to change? Okay, those references would come from the primary control. And then the reference to the primary will come for the secondary control, like that. So this hierarchy will be maintained. Why this hierarchy is important is this, because usually otherwise there will not be any power sharing. The power sharing can get badly affected if you do not use this approach. For example, if I ask you just very basic simple question. Let's say you have 2 sources or 3 sources, any number of sources. Those sources are electrically connected, and then there is a load. Okay, that load is drawing power. Now, from which source the load will draw power? For example, let's say this is source 1, AC source 1, connected here. There is a line in between AC source 2, AC source 3, something like this, and there is a load here. And they all these sources regulate the voltage here, VOD star, VOQ star. They have a regulator voltage here. Okay, this is the case. They all have regulator voltage here. Now the load is drawing power. From which source it will draw the power? The thing is, the current always takes the least impedance path. Here is a lot of impedance in between. While this source can directly give power to the load. So obviously the other source may give some power, but what will happen that this load will take maximum of its power from the topmost source shown in this picture, while the others may not be properly utilized, and this may lead to instantaneous overloading. Even not steady state overloading, it may lead to instantaneous overloading of the source. Why? Because let's say there is one load. Let's say suddenly the second load comes up. Suddenly let's say the third load comes up. Like this if it happens. And let's say all the loads are coming at the same point here only. What happens? they will overload the first source while the other would be underutilized. So that is not something we want, and that is why the primary control comes into picture. The primary control kicks in, and what the primary control does, it will say no, doesn't matter. It doesn't matter where the load is connected. What we will do, we will do something that all the sources give power to that load. What that means? What that means, the primary control will do something that the power is intentionally forced from the bottom sources. All right. How would the bottom source throw power to the top? You know, the power in AC system flows from a leading angle to lagging angle, because you know the power is EV by X sine delta. Yes. So if the delta increases, what will happen? Your power will increase. So that means you have to increase the angle of the bottom sources. Now if you have to increase the angle of the bottom sources, how can you increase the angle? By creating a temporary frequency difference. Remember, I am saying temporary frequency difference, I am not saying a permanent frequency difference, because that is not possible. In an AC system, you cannot have two different frequencies as steady state. Why? Because as soon as you have a frequency deviation, it's a transient, it's not a steady state. Why? Because as soon as you have a frequency deviation, there is the integration omega 2 minus omega 1 dt leads to change of angle. Correct? That change of angle will lead to power flow. So that means the three system diagram that we just discussed here, if we have to throw power from the bottom to top, we have to do something that the angle of the bottom sources starts to lead the angle of the top source. How can we do it? We can have the bottom sources at a slightly different frequency, or in other words, the top source at a slightly lower frequency. If so happens, then the difference of frequencies will lead to an angular difference, and that angular difference will push power, okay, and that power will flow due to EV by X sine delta. So now the bottom source is pushing power. Then what is the choice left with the top source? The choice is that, well, there is more power coming, I have to reduce my power. So they will come back and they will manage such that they share the power equally, right? So that is the whole concept, that by intentionally changing the frequency of the source, we create an angle difference, or we increase or decrease the angle, that leads to power flow and the power is shared. So that concept of intentionally changing the frequency or voltage magnitude for that matter is the primary level control, and there are various types of primary level control, but the common one, which is basically to change the frequency, is called the droop control. So the common one is the droop control. Droop control means intentionally you will change the frequency of this source by the equation and by the diagram shown here. Now, can you intentionally change the frequency of an inverter, or for that matter, can you intentionally change the frequency of a synchronous generator? The frequency of the synchronous generator is governed by the swing equation. Accordingly, the frequency will be decided. In an inverter, you just have to give a theta by integration of some frequency, and accordingly the reference signal for PWM will be produced at that frequency. Yes, right? In the last lecture we discussed, you put a constant omega, integrate it. That means the reference will be generated will have a frequency as good as that constant omega. Correct? So now the question is, instead of having a constant omega, let's use a omega which is a function of power. As you see here, this is function of power. Okay? As the power increases, as my power increases, I go on this axis, my voltage, my frequency starts to come down. So take for example the previous case when you have source here and here. Initially this source is giving more power because it is electrically closer to the load. What happens then, its frequency we are forcing to come down due to this nature. We are forcing its frequency to come down. What happens then? The bottom one, which is at a higher frequency, its angle starts to increase, because angle is integration of the frequency difference. So this is at high frequency, so relatively this angle will start to lead. As soon as this angle starts to lead, there will be a power flow. The power will start to push. The power will push. The top one obviously has to then, what happens? Reduce its power, because the load is fixed, and at some point they will come to equal power. And that is how the power sharing is achieved. Okay. So mathematically, if you see, if this is the equation of one source, you can have same equation for all the sources. Okay. So let's say for any source I write omega I equal to omega nominal minus m I p minus p naught I. For any ith source, you know, at steady state you cannot have two different frequencies. So for any omega I, there has to be omega j equal to it for other sources. That means omegas for all the sources would become the same. So let's take for example two sources. Okay. So then what happens? Omega 1 equal to omega nominal minus m1 p minus p naught 1. Omega 2 equal to omega nominal minus m2 p minus p naught 2. Like that. Now if we keep the slope same, m1 and m2, if these slopes are same, then you know at steady state these omegas have to be equal. They cannot be different. Omega 1 has to be equal to omega 2. Let's say omega nominal, the nominal frequencies are same, so they will cancel out. Let's say m1 and m2 are also same, so those m's will also cancel out. What will happen? Your p1, so this is basically for the first it will be p1 minus this will be p2, right? So now if I say if m1 is equal to m2 and p01 is equal to p02, then what will happen? Can you see this equation? The only unknowns are p1 and p2, so the p1 and p2 will become same. So automatically you achieve the desired power sharing. That means you avoid instant overloading of the first source and you avoid equal power sharing. Okay, so the powers are equally shared. Now, just one small just information here. Usually when you implement this, what happens? You see the variable is p, power, m p minus p naught. So x-axis is p. This is not the measured p, but this is the filtered p. So the measured p that you measure from the sensor, the voltage and current, you pass it through a filter, because you want to remove the noise associated with the PWM or the noise associated with the sensors. So to remove that noise, you pass it through the filter. Okay. So this P that you see here is a filtered power. So when you implement it, you have to put a filter, and the filter will lead to some kind of stability issues, because the filter always introduces a lag. Correct? So that is very important to understand. Well, for now, so that power is you give to this equation. The frequency changes lead to angle change, the angle changes, the power changes, and the power is achieved between multiple sources like this. For example, here two sources. Now, but what happens here, what we are told is that when you change the frequency, the integration of omega 2 minus omega 1 dt is basically your angle, right? So by changing the frequency, what you do, you change the angle, and you change the angle, that means the power flows. The concept is the power has to flow by changing the angle. And how does the power flow by changing the angle? The power flows by changing the angle by the relation P equal to EV by X sine delta. That means when the angle changes, the power has to change, and by the relation EV by X sine delta. But this is valid only if your line is purely inductive in nature, that means the high voltage system. But if you again talk about a distribution system, a microgrid or a low voltage system, then what happens? The line is no more reactive, this formula is no more valid. If this formula is no more valid, what is the case? As we already discussed this, both active and reactive power affect both voltage and frequency. There is a coupling between the term, right? So then we to consider this case, we put a generalized droop equation which considers droop in both. So now you see here in this equation, just like frequency, I have done write another equation from the voltage magnitude. The voltage magnitude equal to V nominal minus NQ minus Q naught. Correct? So the voltage magnitude is Vn minus NQ minus Q naught, just like frequency is equal to omega nominal minus MP minus P naught. Okay. So it is clear from this equation that the frequency is related to power and voltage is related to reactive power. That is the case with the traditional or the high voltage system. But when you come to a microgrid level, you have both voltage and frequency, active and reactive power affecting both voltage and frequency. So you have to take that thing into feature. Okay. So if you take that thing into feature, you write a new droop equation which is called a generalized droop equation, where V magnitude, the magnitude of the voltage, and this is the voltage magnitude which we give to our VOD star. D axis voltage reference, while Q axis is 0. So this voltage magnitude we give as the reference to the controller. This is basically V nominal minus NQ, Q minus Q naught, because both voltage and both active and reactive power are affecting both voltage and frequency. So we'll have terms of both. Okay. So here you have this term NQ, Q minus Q naught in the voltage, and there is NP, P minus P naught in the voltage. Likewise here MP, P minus P naught in the frequency and Q minus Q naught in the frequency. But then one of them will dominate if the line is more reactive or more resistive, right? To add that feature, weighing factors are given. So these are weighing factors. These four are your weighting factors. That means you put more weight. For example, let's say the line is purely reactive in nature, X. If the line is purely reactive in nature, that means what will happen? This X by Z will become 1. R by Z will become 0, right? So if R by Z becomes 0, let's say this term goes away. That means voltage is just related with Q. Likewise, this goes away. That means frequency is related to X. So this is one important point to note. Second important point is that because it's a drooping kind of nature, the frequency and the voltage are dropping as the active and reactive are increasing. So the nature is droop. Therefore, we have a minus sign here. If you see the generalized droop, we have a minus sign here, we have a minus sign here, we have a minus sign here. But then here we have a plus sign. Okay. Now why we have a plus sign here? Because the nature is opposite. How reactive power Q affects frequency? Reactive power Q affects frequency. How is it? Is if you have to do a complete derivation. So you should derive the expression P equal to EV by X sine delta. You know this expression? This expression is valid when the line is purely reactive in nature. What if the line is purely resistive in nature? R. Then this expression is no more valid. You have to derive exactly the same way you derive this expression. Once you do that derivation, you will figure out that it also carries on minus sign. So here it is P equal to EV by X sine delta. Then it will be a minus sign as well. That means the nature is opposite. Okay. Here delta increase means power increase. There delta means delta increase means Q decrease will have a minus sign, because this Q with delta, delta is nothing but integration of frequency. F omega integration is angle. So if P is related to delta, that means P is related to frequency. That is why P is related to frequency in a normal inductive line. But in a resistive line, Q relates with frequency. So that relation you have to derive. And when you derive that relation, you get a minus sign with it. That minus sign shows that no, you don't have to droop. You have to rather increase, the nature is opposite. Okay, and that is why here we are carrying a plus sign. Alright, so this is the effect of droop, that by intentionally changing the frequency. So I am not going into the generalized one, I am, let's say, talking about a simple droop like this one. By intentionally changing the frequency, we are making the inverter share equal power. Why? Because at a steady state you cannot have two different frequencies. So omega 1, if let's say there are two sources, three sources, omega 1 has to be equal to omega 2, has to be equal to omega 3, has to be equal to omega n. And if their amps, droop slopes and P naughts are same, then at any given load, P1 will be equal to P2 will be equal to P3. The fundamental concept is that the frequencies have to be same. But that is not the case with the voltage. In a system, you can have different voltages at different system. For example, one bus is 1 per unit. You do load flow study. Load flow, at the end of load flow study, you get the voltages, right? One bus can have 1 per unit, other can have 1.05 per unit, other can have like 0.99 per unit. So the voltage is no more a universal variable, which has to be equal. So although we apply droop, the reactive power is shared, but there is no guarantee that it will be shared equally always, because the left hand side is not, the left hand side of the equation need not be same for all the sources, while for frequency left hand side is same for all the sources. Clear? So the whole point is, by changing the frequency like this, what we can do, we can change the angle to change the power flow so that the powers are shared equally. Okay. So this is the primary control. So summary is, what are we doing in the primary control? We are intentionally changing the frequency of the sources so that whichever source is giving more power, its frequency falls faster, so that the other source starts to feed power and the power balances and the frequency balances. So the concept is that we are intentionally decreasing the frequency. But you know, in a system you always want a regulated frequency, for example 50 Hz. Now here we are intentionally decreasing the frequency. So we have to increase the frequency now. Now the question may come, if you have to increase the frequency, why in the first place we decreased it? So the decreasing was necessary to ensure that we share the power equally. That was, we had no choice, but we had to do it. Once we have done it, now what we can do to restore the frequency? We can do is that for all the sources, we shift the characteristics up and down. So you see this graph for any one source, this one, keeping the slope same. If you move it up and down, the slope, this characteristic, that is basically the nature of secondary control. Okay, so secondary control, what it is doing is, it is shifting the curve up and down, just like you see here. Okay, so now here what we are doing is, here you have this characteristics, the omega equal to omega nominal minus MP minus P1. Let's say the inverter is operating at this power, is this point first. It is giving power P1 and it is producing the nominal frequency. Okay, this is the operating point. Then let's say there is a sudden change in the power demand and it goes to point P2. If it goes to point P2, then this would be your operating point. Correct? So this would be your operating point. Now this operating point, at this point you see the frequency is less. Okay, at this point the frequency is less, the frequency is reduced because we have intentionally reduced. So what we are doing it, we add a correction term that is like this shown here. We add a correction term delta omega and we shift this characteristic upwards, so that at this new power P2, we again are able to operate at the nominal frequency. And this shifting has to be done in such a way that the relative equal power sharing that you have achieved is not lost. So the objective of the secondary control is this: limit t tends to infinity omega it equal to omega nominal. That means within a finite time, your frequency should be restored to nominal. Limit t tends to infinity, mi pi equal to mj pj. That means at somewhere before steady state. Limit t tends to infinity means somewhere at a steady state. What is that steady state? 1 second, 2 second, not saying. At steady state, mi pi equal to mj pj. For each source, जितने भी हैं microgrid में 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For everyone, mi pi should be equal to mj pj. Now, if mi equal to mj equal to m, let's say, if that means we are keeping the group same. So m cancel out. What is left with pi equal to pj? That means for every I and j in the system, every ith and jth source will have the same power. Okay. Similarly, for reactive power, limits t tends to infinity, ni qi for the ith source becomes equal to nj qj for the qth source. Okay. But then there comes the interesting thing. In a AC system, you cannot control voltage, magnitude, frequency, PQ. 4 variables: voltage, magnitude, frequency, PQ. You cannot control all these 4 together. Not possible. You want that I want this much power, this much reactive power, add this much voltage, and then at this frequency. Not possible. Somewhere you have to give a relaxation. Then the system has to automatically come to an operating point. If you are forcing an operating point, which is not the natural operating point of the system will collapse, right? So that is why if we are controlling the frequency to the rated value, nominal frequency 50 Hertz for example, if we are saying the power has to be balanced, if we are saying the reactive power has to be also balanced out, then the fourth variable we have to relax. And the fourth variable is the voltage magnitude. And therefore, what I am writing here is, you see, the limit t tends to Tf, that means again within a finite time the voltage should be nearly equal to nominal voltage, but it is not showing that it has to be exactly equal to the nominal voltage. Some relaxation has to be given. Either you give the relaxation in the reactive power, then regulate the voltage, or you give relaxation in the voltage and share the reactive power. So one of them has to carry a nearly equal sign. Okay. While the other can carry a equal sign. Okay. So the frequency restoration and the voltage restoration has to be done within a finite time duration, and therefore the limit t tends to Tf, finite time. The sharing has to be done at steady state, whatever that steady state is, and therefore the limit t tends to infinity is given. So how do we do this? How do we achieve these objectives? These objectives are achieved by adding this delta omega. So the Drup equation will now change. Omega equal to omega nominal minus mp minus p naught plus delta omega, and likewise for the voltage plus delta v. So one variable, then this variable is called secondary control variable. Sometimes this nominal and this are added together to make a new variable like omega star. Okay, that is also fine. You will find papers or literature with both the two approaches. Okay, so that is the action of the secondary control, is to either give this delta omega or omega star. Some variable you have to get from the secondary control. The question is, how do you get it? Because it is just not one source. Every source has to get this variable, and we have to maintain the power sharing. But let's say there are like two sources. Each one of them don't know what the other guy is doing. It is shifting. Let's say they know that both of them are shifting their characteristic upwards. How much they are shifting? The other guy doesn't know the first person. The first person doesn't know the second person. So what happens then? The power sharing can get affected. So you have to shift, you have to maintain the power sharing, and that is why the secondary control has to be done in such a way that this variable delta omega or omega star has to be obtained in such a way that you maintain the power sharing, and that means you have to know each other's information. Okay, and therefore the communication comes into picture. So the secondary control is basically implemented using some communication techniques. Based on the type of communication, we have secondary control architectures of 3 types called centralized, decentralized and distributed. In the centralized one, what we have a central control. There's a microgrid main central control. It takes communication from all the sources. Okay, so you see the arrows. This shows the information is sent to the central controller, and the central controller gives command to the primary controller. Okay. The problem is, this is a very communication infrastructure intensive control approach, because all of them have to send the data to one center, and from the one center all data will come. So there is a lot of communication involved, okay, and it can lead to failure, because let's say if there is a failure, communication failure here in the central control, then all the downstream bodies will fail to operate. So this is not a good approach, because it's very communication intensive. The next one is a decentralized control, and there is no communication. A primary, secondary, everything is with oneself. Each source has got its own primary control, has got its own secondary control. So what I've written DG here is distributed generation. Okay, distributed generation 1, distributed generation 2, distributed generation n, and they all have their primary control and the secondary control. The thing is, if they have their own primary and secondary control, they have to get this variable delta omega at their own, without knowing others' information, and that is challenge. If there is even a minute difference in delta omega, then at that point the power sharing will be lost. And therefore, although the good part here is that you don't need any communication infrastructure, the failure of chances are less in that term, but the failure of chances in the other term is there, because you don't know the others' information, then there are always chances of failure. Okay, but still there are some ways to do it. For example, one way to do is use a washout block. Okay, so instead of just using this omega equals to omega nominal minus mp minus p naught, multiply a transfer function which is s upon s plus kp. This transfer function, this is called a washout. Why it is called a washout? Because it washes out the signal at steady state. Apply a final value theorem. You all must have read it. When you apply the final value theorem, this signal becomes 0. This signal becomes 0, that means the whole multiplication actually becomes, this whole multiplication becomes 0. So omega becomes equal to omega nominal. Okay, that means what? That means during transient, so this is becoming 0 at steady state, but during transient it is not 0. So during transient it is giving subsignal. During transient the frequency is getting changed. As the frequency is getting changed, the power is shared. Once the power is shared, after that gradually the signal washes out and the frequency is restored. But the thing is, the washout has to happen once the power is shared. But because there is no information, they don't know whether the power is shared or not. And that is why these things may fail. This type of control may fail. So we have discussed two types of control approach. One, with complete communication based, performance wise it will be good, but the failure can be with the communication. Second, no communication. So there is no chance of communication failure, but performance wise it can be affected. So a compromise of the two is called, the third one is called the distributed control. And in this one what happens, there is communication, but the communication is not with the central body, rather the sources talk with each other. Okay, so you just communicate in your information to the neighboring secondary control. So you see the arrows where the communication is being sent. So one entity, one source, one distributed generation sends its information to the neighbor, second gives to the third to the fourth to back to the first, like that. So the communication is connected. So there is communication, but there is less communication. So chances of failure are less. This way we know each other's information, and then we can achieve the desired control. So how do we do that? Let's see a little bit of mathematics now. Okay, so this is the concept behind this distributed control. How do we implement it? We go for a approach that there are certain number of variables that has to be communicated among the sources, and some mathematics has to be developed. So in the remaining 15-20 minutes, we'll just try to focus on this mathematics. I'll keep it very introductory here, so that you understand it and then you can read later. Okay. So let's say you have a microgrid having n distributed generators. Once you have a microgrid having n number of distributed generators, they all have some certain state variables. You know what our state variables are. X dot equal to ax plus bu. Okay, and then there could be some disturbance term. So x dot equal to ax plus bu plus d terms, some disturbance terms. Okay, so let's say the differential equation is basically given by here x1 dot is equal to ax plus d, so the differential term plus bu. This is your differential equation. Y equal to cx, your output matrix, typical state equation, right? Now your x represents your state variables. Okay, x belongs to real numbers. So you see the mathematics that is here, x belongs to this r symbol, n is written over here. It represents a nth order real because there are n generators. So xi represents a state variable or a state array of ith source, and there could be n such sources, and all the states are real numbers. You know that, right? Voltage, current, instantaneous voltage is always real numbers. Be it voltage, be it current, power, frequency, these are all real numbers. Okay, so these xi's belong to a state of belong to real numbers having this order n corresponding to it. Okay, likewise control inputs ui also belongs to real numbers, and output variables obviously also belong to real numbers yi. Okay, now these are the state, this is xi. The equation that I have written here in terms of I represents the state of or output of ith source, any ith source, in general 1, 2, 3, 4, 5, 6, any ith source. Now as we discussed here, there will be communication from this to this, this to this, this to this, like that. Okay, so first to second, second to third, like that, or maybe second to first also, two-way communication is there. Okay, so I to j, any ith source will communicate to jth source, and what we try to achieve then, we try to achieve a cooperative control. We try to achieve a consensus between the outputs. That means the control will work on this principle. We develop a control objective which is called a cooperative control objective, where limit t tends to infinity. That means somewhere at before the steady state, yit minus yjt norm becomes 0. So norm is basically error, right? If it's a single variable, you just take error. Error can be positive or negative. When you have multiple errors, you cannot just add errors, because let's say one error is negative, second error is positive, you add them to, it becomes 0. Wrong. This should not happen. What you do is you take an absolute value. Error of first, error of second, absolute value becomes the total error. So rather than taking absolute value, we actually take norm. You all must have read norms in basic mathematics, right? So the norm of this should go to 0. That means all the respective individual errors should go to 0. That means, for example, frequency error omega 1 minus omega 2, power sharing error m1 p1 minus m2 p2, or reactive power sharing n1 q1 minus n2 q2. All of these individually errors should go to 0. If so happens, that means omega 1 is equal to omega 2, m1 p1 equal to m2 p2, n1 q1 equal to n2 q2. That means your objectives are met. So our objective is to achieve this. At steady state, the norm between yit minus yjt should be equal to 0. How do we achieve this? So what I have done here is, this represents your system. Okay, this represents your objective. For this system, we have to have this objective. How will we do it? Then we will go for graph theory. Okay, so we say a digraph. A digraph means a directed graph. Okay, that means information is, in simple terms, information is sent from one to another with certain weights. Okay, so the graph is mathematically represented by a node, by edge, and adjacency matrix. So node means what are the nodes in that graph. Okay, for example, let's see, one node here, one node here, one node here. There is some communication, some information is sent like this. So each entity which can communicate is basically called a node. So if there are n sources in our microgrid, we'll have n number of nodes. Clear? So as you see here, we have these n number of nodes. Then we have edges. Edges represents the communication channels. For example, these are the edges. Okay, like that. And then we have a adjacency matrix. Adjacency matrix represents basically A, I, J. For example, first is communicating with second, so A12 will be equal to 1. Let's say first is not communicating with third, so A13 will be equal to 0. So this is how you define a graph. Okay. Now what happens now, through the graph, through the edges and at different nodes, you communicate all the signals as per your Aij matrix. Once you receive that communication, you compare with something and you create an error, and that error goes to a controller. That can be a simple PI controller, and that controller would generate your variable that we have talked about, this variable, either delta omega or together as omega star. So the summary is, through the graphs, we send the communication, we receive them, we create an error, we compare them, this minus this, or this minus this plus this minus this, something like that. That error is created, is given to a PI controller. That PI controller then generates the desired secondary control variable, right? So what we have discussed so far is, okay, good. Now we know what graph theory is. Now we know these x, which are the state variables, will be transmitted, will be received by other person. So xi, xj, right? You can say sending one is xi, receiving one is xj. Then you create an error and then you pass it through a controller. The controller will then give command. That is very simple. The only difficulty then comes, how do you create that error? You have xi, you have xj. What will you do with those xi's and xj's to create the errors? For that, there are innumerous number of methods. It's not just one I can tell, but in the last 5 minutes or so, I will just discuss 2 of such methods to give you the idea, and then you can continue. Okay. So one such method is called average based distributed secondary control. So the whole point is, these are called consensus control. Consensus means like 2 people talking on something, they come to a reach or agreement, to a consensus. Like that here, 2 entities, they have the state variables, which either they try to bring the state variables together to a certain value, to a consensus, to an agreement. So that consensus based control we have to achieve. How do we achieve? There are different ways to do it. For example, let's say the first is average based distributed secondary control. That means here we are trying to make the average equal to the reference. Like say for example, there are 3 numbers. Okay, let's say for example, 1 is 2, 1 is 3, 1 is 4. Let's say. Okay. Now their average is coming 3. Okay. Let's say the desired average reference is also 3. So average is meeting, but individually they are not meeting to 3. So that is why if you just talk about the average, you may have errors. Although theoretically, when you say that if each of them reach that same value, they become same as the average. So the concept is to make the average equal to the reference. If you make average equal to the reference, you assume that all of them will be at the same value. But sometimes this may fail also. But the theory behind average based consensus is this. Let's say the reference value of xi, if you see this, let's say the reference value of xi be x star. Okay? Then how do you get the control variable? You get the control variable by passing through the controller. So KIS is the controller and you generate an error. And what is the error function? Error is your reference value minus the average value. What is the average value mathematically? Mathematically, average value is the summation of all the states divided by the number of states. So this is how you get one average based approach. Another one is called consensus based distributed secondary control. That means you try to have the consensus between all the states. That means x1 minus x2, x2 minus x3, x3 minus x4. Like that, all the errors should become 0. So mathematically, how do you write it? Again, this is your output variable, the control variable that you want to achieve. KIS is your controller transfer function like Kp plus Ki by S. The important thing is you are making an error function. Like here, this term is your error. Okay. Similarly, here you make an error function. So the error here is summation of j, while j is not equal to I, aij xj minus xi. So aij xj minus xi. What does this mean? Aij, I told you, wherever there is communication, aij will be equal to 1. Wherever there is no communication, aij equal to 0. So if there is no communication, that term is anyway 0. Wherever there is communication, this aij will become 1. So let's say a12 is 1. So x2 minus x1. Likewise, let's say let's say the second source, for example. Let's say the second source is talking with first as well as is talking with third. So A21 and A23, both terms are there. So the error would become, the total error would become x2 minus x1 plus x2 minus x3. Like that, whatever is the number of communications you are receiving, all errors have to be added up. So therefore, there is this summation sign. Clear? So this summation represents all the errors has to be added. You get a resultant error. When the error becomes 0, how would the error become 0? The controller will make error 0. And when will the error become 0? Error will become 0 when your xi becomes equal to xj's. Correct? Now, as I told, some can have negative error, some can have positive error, the error may cancel out. So you can take the absolute value, you can take the norm, those things are there, but basically xi minus xj. So when the error becomes 0, that means x2 minus x1 is equal to 0, that means x2 equal to x1. x2 minus x3 equal to 0, that means x2 equal to x3. Alright? So like that we achieve consensus. Now here is the problem. Although we have achieved consensus, although we have made all the states same, but we don't know at what value we have made them same. For example, let's say voltage reference. Let's say you have to restore the voltage. Voltage are same. Let's say 400 volt 3 phase AC, or 380 volt 3 phase AC, or 420 volt 3 phase AC, or 440 volt 3 phase AC. Okay. At what value you have to make same? Then you have to also give additionally the reference. Now the thing is, it is not necessary to give the reference to only to all of them. You can give the reference to only one of them. Why? Because as soon as for any one of them, it matches with the reference, and then there is consensus, so automatically the other will match with the references. So then in this error term, we add another term, which is gi xi minus x star. And gi is called a pinning gain, which is again gi is equal to 1 only for that source for which you are giving the reference. Okay. For example, let's say 5 people are walking, and the first person, if you told that you have to walk at this speed, and rest you tell you have to maintain this much distance, automatically the rest will have the same speed as the first one. So first one gi equal to 1, for others gi equal to 0. Alright. So this is how consensus based distributed secondary control is implemented. At the end of the day, your objective is to get those variables delta omega or delta v. Okay. Last 5 minutes. Very quickly, I'll just discuss, not in detail, a little bit about DC microgrid. As I told earlier, DC microgrid, why they are important, particularly for such areas where there is no power system, you can have DC microgrids because they give you the benefit of less convergence, and synchronization is quite easy. When you talk about AC microgrid, you have to synchronize voltage, magnitude, frequency, phase angle, all three. Here you just have to synchronize voltage, that's it. Then in AC there is a bigger problem of reactive power management, right? Here there is no reactive power management, okay? So here the concept remains same. You have the inner loop, which is your device level control, V star, that you control. Then you have the primary, you have the secondary. The primary is same, the droop control, the variable drops, and then you try to achieve the power sharing, okay? And the secondary is basically to restore. So here, see, in there was a voltage was frequency, voltage, magnitude. Here there is no frequency thing. Here there is only voltage, magnitude in DC. So therefore, in DC, we go by this droop equation, V reference equal to V nominal minus DI. Slight difference, D is the droop gain. A slight difference here is there is no power variable. Compared to the power, like omega equal to omega nominal minus MP, the input variable was power. Here we don't use power, here we use current. Okay, so there is altogether different story why we use current. There is no much time left, so I cannot discuss here, but I'm okay to discuss off the records. Okay, but in DC microgrid, if you have to imply droop, we go for current based droop. Okay, now when you implement current based droop, the equations is like this. For example, let's say you have a two source DG1, DG2. They are connected through R line. There will be a line in between. It's a DC, so you will have only resistance, no inductance. And you have R load. Okay. Now what happens, if this is the output voltage VO2 of the second, output voltage VO1 of the first, you can write equation for the load voltage in terms of these two. So here we draw the curve with respect to this V load versus I, and if I draw V load versus I, you can draw separate two curves for the two sources, because both of them will give one different equations for V load. For example, if you see for this second load, it is second DG, it is directly connected across the load, so VO2 equal to V load, while for the first one VO1 minus the drop in the line equals to V load. Alright. And then VO1 and VO2 itself have the droop equation, which is given by this V nominal minus DI. So effectively for the first source, it will be V nominal minus DI minus R line I. For the second, it will be just V nominal minus DI. So what happens, you see, if you see this kind of nature, and at the end of the day, you can have only one load value, load voltage value. You cannot have two different load voltage values for the load voltage, right? Load voltage will have one value at steady state. So wherever it is, it will intersect these two curves at these two lines. Accordingly, you will get two different current values. So this is your I2, this is your I1. So here the sharing is difficult. There is always an error. So how can you make an error less? If you increase D, because see here D and R line are added. If you increase D very high, so that the effect of R line is negligible. If the effect of R line is negligible, then you can say assume both to be directly connected across the load. That means you can say both will share equally. So that is only possible when you have a D which is very high compared to the R line. But if you have very high D, that means you have a slope which is very high. Now you have a slope which is very high, then the voltage will fall a lot, and therefore DC microgrid with just primary control is usually not used. You will always have a secondary variable. Okay. Now whether it is DC microgrid or it is AC microgrid, your droop slope will define how your system will perform. Right? And you remember when you talk about the stability problems, I discussed that the power sharing controller leads to low frequency oscillation. So it was basically those low frequency oscillations come if you do not select the droop gain properly. The slope is not set properly. Okay. So for that, what I have planned is on the afternoon session, we have a tutorial where we work on MATLAB Simulink. I will guide you to how to develop a inverter microgrid. Work with me and see how the effect of droop introduces low frequency oscillation in the microgrid. Okay. So I will give you the instruction regarding that later, but first, for now, let's close this topic today. And if you have any questions, please tell me. Good.